Welcome to this explainer. Look, if you're a software engineer gearing up for a technical interview right now, you already know the stakes are incredibly high. The difference between landing that killer senior developer role and getting a polite "no thanks" often comes down to one specific thing: systems architecture. And in the architecture world, absolutely nothing is quite as foundational, or honestly as frequently tested, as the solid principles. So today, we're going to demystify these core concepts and look straight at the source code patterns you absolutely need to know.
Okay, let's dive right into this. Here's our roadmap for today. We'll start with the solid interview itself, then hit the single responsibility principle, open/closed principle, Liskov substitution principle, interface segregation principle, and finally, wrap up with the dependency inversion principle.
Section 1. The solid interview. Mastering the most frequently asked architecture questions.
Section 2. Single responsibility principle. The S in solid.
So understanding the high-level concepts and knowing the exact terminology behind this acronym is literally the key to passing senior developer interviews. Interviewers, they aren't just looking to see if your code runs. They want to see if it can survive, if it can scale, and if a whole team can maintain it without it turning into a totally tangled mess. The formal definition of the single responsibility principle, or SRP, is that one class should do only one thing at a time. It sounds incredibly straightforward, right? But man, it is surprisingly easy to violate this rule when you're deep in the trenches writing code. We really need to ground ourselves in this core rule before we even open an IDE.
Let's think about this practically for a second. Ask yourself, should an employee class calculate its own salary? I mean, think about the real world. If you look at an employee in a company, do they calculate their own payroll, figure out their own tax brackets, and then issue their own checks? Well, no, of course not. The accounting department handles that whole shebang. Your code should reflect that exact same reality.
And this brilliantly illustrates what we're talking about. Take the notorious God class approach. An employee class trying to juggle a name, an ID, a task, and calculating the salary, it's just doing way too much. But if we cleanly segregate this, the employee class strictly handles identity and tasks, while a totally separate salary calculation class handles the payroll. By breaking this up, if the tax laws change tomorrow, you only update the salary class. You don't risk breaking the core employee data. It's just so much safer.
Section 3. Open/closed principle. The O in solid.
Now, this principle is all about preventing that dangerous ripple effect you see in aging code bases. The open-closed principle dictates that classes should be open for extension but closed for modification. I really want to emphasize that second part, closed for modification. The underlying philosophy here is simple, but it is profound. If code is already working perfectly, if it's testing well, and it's deployed in production, do not touch it.
Think about the sheer panic of this scenario. What actually happens if you modify a base salary calculation class that is currently being used in, say, 1,000 different places across an application? If you just jam a new if-else block directly inside that core class, you suddenly need to run a massive impact analysis. You've got to rerun unit tests across the entire system. Just one tiny typo could trigger a 2 a.m. pager alert and bring the whole application crashing down. It's literally every developer's worst nightmare. So here's how we completely avoid that nightmare. The wrong way is modification. Say you get a new requirement for a manager role. The bad instinct is to dive into the original class and stack another if-else statement onto the pile. The right way, though, is extension. Instead of touching the old class at all, we create a brand new salary manager calculation class that simply inherits from the base class. The brilliant part about this? Any new client needing manager payroll just uses the new class, while the thousands of old clients relying on the base class remain completely undisturbed.
Section 4. Liskov substitution principle. The L in solid. Named after the pioneering computer scientist Barbara Liskov, this principle demands that a child class must seamlessly implement all methods of the parent class without any side hacks. Simply put, inheritance goes terribly wrong when a child class tries to subtract, disable, or just avoid properties it inherited from its parent.
To really lock this concept into your memory, I want you to think of the classic duck test. It looks like a duck, it quacks like a duck, but it needs batteries, right? A mechanical toy duck might inherit from a base duck class because it looks and quacks like one, but fundamentally, it fails to act like a real, living duck. It forces a weird, unexpected exception into the whole system.
Let's see how we actually fix a Liskov problem in real code. A typical hack looks something like this. A contract employee inherits from employee, but since contractors don't get health insurance, the developer lazily throws a not implemented exception for the insurance property. That is a massive red flag in an interview. We don't fix the problem with a hack. We fix it by restructuring the base class itself. We create a clean base employee with absolutely no insurance. Then the contract employee inherits perfectly, and an internal employee inherits but adds the specific insurance feature. We fixed the root abstraction.
Section 5. Interface Segregation Principle. The I in solid.
This principle focuses heavily on keeping our interfaces lean and highly targeted. Client code should not be forced to depend on methods it does not use. When you create massive, bloated interfaces, you essentially force completely unnecessary dependencies onto the client code. And you know what that does? It clutters up the application and creates totally avoidable security and architectural risks. To see this in action, just imagine a monolithic interface. Let's call it an iCRUD that forces any class using it to implement add, update, read, and delete. But what if you have a simple reporting controller that literally only needs to display data? Forcing it to carry delete methods is actually pretty dangerous. The segregated alternative is splitting out a focused iRead interface. Now, our reporting controller happily and safely uses a streamlined interface that exactly matches its needs, making the whole codebase drastically safer and cleaner.
Section 6. Dependency Inversion Principle. The D in solid.
Okay, a quick, massive warning right here. Do not confuse dependency inversion with dependency injection during your interview. They are definitely related concepts, but if you mix up the acronyms, it's a huge red flag for the interviewer. Dependency inversion itself dictates that higher-level modules should not depend on lower-level modules. Both should depend on abstractions. Basically, what we want to do here is completely eliminate tight coupling between the different levels of our application, so we can swap parts out later without, tearing down the house.
Let's map this out in practice. In step 1, you have your higher-level module, like a home controller, that needs to fetch some employee data. If it ports directly to step 3, the lower-level concrete employee classes, well, now they are tightly coupled. So we insert step 2, an abstraction, like an iEmployee interface. Now the home controller just asks for the interface, and the concrete classes implement that interface. The dependencies are completely inverted, and that tight coupling is severed.
So the absolutely crucial point is pulling all of this knowledge together. Here is a quick summary checklist for your solid interview prep. First, know the exact acronyms. Precision really matters here. Second, when they test you on Liskov, avoid using empty properties or those lazy not implemented exception hacks. Third, remember not to confuse dependency inversion with dependency injection. And finally, if your abstraction is bad, don't patch it, fix it right at the base class root.
Which leaves us with one final thought today. You've mastered the theory and you've seen the underlying code structures. But how will you actively apply these architectural secrets in your next technical interview? Because look, it's one thing to know the letters, it's a totally different beast to write the code out on a whiteboard under pressure. So keep practicing, keep refining those abstractions, and good luck out there. Thanks for learning with us today on this explainer.